All right, so today we're taking a look at volumes of solids of revolution. You should have a handout in front of you. If you don't have that handout, it should be available on the website. If you look at mrmathwell.com here, let's see, is it up there? There will be some notes up here. So here we go, cross sections, volumes, solids, notes, and assignments. That's the one right there. So that's the note package I'll be working from today. Okay. So we've talked about cross-sectional solids, right? That was the last lesson we did. And if you consider over here, this being the graph, it looks like some kind of quadratic, right? From A here to B. Now, if we were thinking of cross-sectional solids, so a volume of some kind of solid where, you know, we had a cross-section between the graph and the axis, let's say. Okay, we would, let's say if we were looking at squares, these would be squares, right? This is what the squares would look like. All stacked up, right? Squares. Or let's say we were working with not squares, but we were working with semicircles. Remember, we just got finished doing all this, a stack of semicircles of different sizes, and the stack of them would be this solid, right? Well, we're not doing that anymore. Instead, what we're doing is we are revolving an area. So here's an area, and we are revolving this around some kind of axis. So around the x-axis is where we're going to start. So what would that look like if we were to take this area and we were to literally flip it down around, and so it would rotate around the x-axis? Well, it would generate a solid that would look like this over here. So what I'm going to do is I'm actually going to show you a little bit of an animation, okay, from YouTube here. And I'm just going to let this play. And this is some kind of application. And here we have y equals root x, okay? So here's a square root function from a to b, so from 0 to 1. And as I play this, just watch what happens when we allow this function to be revolved around the x-axis, okay? So there would be a solid cone-shaped volume. And as we consider this volume, we can consider this volume to be made up of a stack of infinite number of what? Well, of cylinders here like this. So pies or disks. So this is commonly called the disk method, okay? So that would be like a circular disk. Now this has a very wide width there, okay, just to show you, but as delta x here, as this width becomes narrower and narrower, thinner and thinner, that means that the number of disks approaches infinity. Then we have that solid volume, okay? So right now we're overcounting and undercounting on this one, for example. But this solid would be made up of an infinite number of little disks of different sizes. Okay, so we're going to explore here a different graph. So what happens if we have this? Now, the difference with this one here too is we're allowing this to be rotated around the y-axis. So this is rotated horizontally this way. And so you can see that we have another sort of bullet shape almost, or a cone shape. And that's the disks there, right, are moving up. And so it's just that stack of disks kind of make up this volume. Okay, so here's something that's a little bit different. This is now a region that's contained right here, a region that's contained within two graphs. If we let that rotate around, let's say, the x-axis, you can see how this gets very interesting, right? Now, I don't really know if the disks help us a lot, but just let's consider this. This would be hollow inside here, right? Like this area right here would track, okay, a thick area like my arm would track around the axis like this, okay? Or I guess maybe from your view it would be like this. So it would track around the axis, the thickness of my arm only. And so whatever my arm is actually passing through space, that's what this is, okay? Now we'll let these things play. Notice how there's a gap in the middle. So this is actually referring to what we call the washer method. It's a washer. A disk is a solid sort of circle. A washer would have a gap, a hole in the middle. All right, that's what a washer is. So the disk method and the washer method would both be represented here in these little animations. And of course, As we get out there, you see how thin it gets at the very end point there? Super, super thin. Okay, here's a fourth one. This one is this same thing being revolved around, yeah, a y equals here. Y equals something, right? Maybe y equals 2 or 3. I don't know what it is, but so it's revolving, this way, and it's actually moving through space like this, right? It's not fixed at one point. It's not like this. It's actually moving. Everything is moving around the axis. So we're going to be able to calculate volumes of all of these types of solids here with the methods we're learning today. All right. Now, I don't know if there's one more. There might be one more to take a quick look at here. Yeah, there's another volume of a solid, and this is, of course, rotating around a vertical axis. That's not the y-axis. Same sort of thing. All right. Oh, and there's one more. We'll let the one more go here. All right. So this one right here, so this area right here, if it's rotated around the y-axis, you can kind of see how it fills in this volume underneath there. So all of this space is being covered by this. It's kind of like a bundt pan. Have you ever had bundt cake? I don't know if you ever know what that is, but that's kind of what that's like, eh? Hollowed out in the middle there. Okay. Excellent. Well, we don't need to hear about your advertisements. Close your ears. No, stop. No, don't listen to the commercials. Okay. All right, here we go. All right. Got it? So this one's pretty simple. This is the disk method. But what we're doing is we're taking this point and we're dragging it around. Just like this point is being dragged around the x-axis. And so if you complete that three-dimensional sort of picture here, we get, we get a solid that kind of looks like this, right? And it looks just like this one over here. But we're basically taking those top corners there, like this, and we're pulling them around the x-axis, okay? All the way around and dragging it through space. And everything that it covers, everything that it pulls through is part of the volume. All right. Okay. So if we think about these as disks, right? So here's a disk. Here's another little disk, another little disk. I'm just drawing 4 or 5 or 6 of these disks. But if we consider the sum of an infinite number of disks between here A and here B, right? If we consider an infinite number of disks, that's going to be a definite integral. So the area underneath this curve is an integral, right? Excuse me. Now, if I think about these as disks, remember disks are circles, right? So that's a disk, right? That's a circle. And so what's the area of a circle? Well, the area of a circle, right, is pi times r squared. In this case, the radius of the circle will be equal to the value of the function. So at any point, the radius of the circle is always the value of the function. So pi r squared becomes pi times f of x squared. You see that? F of x is our changing radius. So the sum of all the disks would be the sum of the integral pi r squared. Now I'll explain this axis of rotation. The radius is actually the whole distance from f of x here to f of x here. It just so happens that f of x here, when it's the x-axis, is y equals 0. So you can see how the radius is the difference. Remember last day, let me go back here at last day. Remember the radius or the distance here was always f of x, like it was f of x1 minus g of x, whatever that was, right? It was always the difference between the two functions, right? And so the same thing holds true here as well. Where is it? Yeah. F of x minus the axis of rotation. Here it's going to be g of x or y equals 0. This can be summarized, of course, we can bring that pi outside of the integral, and it looks like this. Let me zoom in. So we have, make sure you have this in your notes, or you should have it highlighted or whatever. I guess you have these notes in front of you. But pi times the integral from a to b of f of x minus the axis of rotation, and that's going to come in handy in a few examples, squared dx. Okay, very similar to what we looked at yesterday. All right, so if we're revolving around the x-axis, please remember that we have y equals 0, okay? Now, this example down here, this expands this, our formula really. It expands how we do things. Up to this point, we've taken the entire area, right, and we've wrapped it around this, this axis. So we get, you know, a solid that kind of covers this three-dimensional flipping. Now, what happens if we only want the solid that's generated by the difference between these two lines, okay? So here's going to be f of x, right? And this is going to be a straight line here, let's say. So this is y equals some constant, okay? Some constant. Now, this is going to be the axis of rotation here still. So here's the axis of rotation, okay? So this can be a constant, it can be another function, but right now this is a constant. So think about this. If we just want to rotate this area that I've highlighted here through space, we are going to have a situation similar to where we started before with the other example, but notice how there's going to be a gap in the middle. You see that? So this is not going to be counted. So what we end up having is we have this poorly drawn cylinder that is blanked out. You see, that's hollowed out. So all of this gets covered, and all the way around the back side or whatever there, right? All of that would get, but there's a hole in the middle. There's a noticeable big hole in the middle, okay? You want to see that? So these discs now become washers. And how you can view this is you basically, you take this area, right? This big area that we have found out before, but we have to kind of subtract, and here in red, I'll put subtract the area of this inner side. And so that's what this represents. It looks a little weird, but it's going to make a lot of sense, trust me, okay? So the volume of what would be this washer, this volume created by a washer, we'd literally have a hollowed out part in the middle. And so you could write this as one big integral. The volume equals pi times the integral of what? The outer function. So in this case, that would be the function that's furthest away from the axis of rotation, the outer function minus the axis of rotation, okay? So that would be the same as what we had above right here, right? That's this whole thing minus the integral of from a to b, okay, which is included all in here in one big, minus the inner function minus the axis. So we're basically subtracting this middle part here, and that just disappeared on me. Okay, fine. So we're subtracting the middle part. That's what this represents. Okay? Okay. So I know that's a lot. Let's do some examples here now. Okay, I think we're ready to do some examples to try and put this into action. So the rotation around an axis is pretty important. So this should be in your notes here. I've kind of got a little bit of this started already for you. So let's zoom in here and let's kind of get going on this. Okay. Excuse me. So in this question here, the axis of rotation is the axis, if the axis of rotation is the x-axis, so in this first case, the axis of rotation is going to be this x-axis right here, or it's parallel to the x-axis, the integrand needs to be in terms of x. So if we are rotating around the x-axis here, this is dx, okay? Now, why is that? A couple things, because the width of this cylinder, the width, this is the differential, right? This is the d something, and it's in the x direction, so that's dx. It's a dx, it's a width of x. What you're gonna find, and again, don't write this down, I don't wanna confuse you too much, but we're going to soon be rotating this around the y-axis, let's say, okay? And in that case, the little differential is going to be y. So this is how we know how our integrand or how our integral is going to be set up, okay? So if we are rotating around the x-axis like this, it's the differential, the little width is in the x direction, so we know it has to be dx, okay guys? That's a big deal, all right? That's the first thing, and that's what that little first part of this says here. The limits of integration then also need to be x values. So consider that if we're going to go from this a to this b and rotate it around this way, well, the a and the b also need to be x, okay? So this is, and I can do this, I guess, x1, x2, okay? So this is all x if the center of the circles or the discs or washers, if that middle, if the x-axis is kind of in line with that, then this is all x stuff, okay? Okay, what else here? So the curves that form being rotated. Okay, all right. Okay, so let's consider this diagram here. And this is a region here that's shaded, bounded by x squared. That's y equals x squared. And y equals x plus 2. Okay. So that's pretty reasonable. We have this region. Now, what are we going to do? We want to find a solid. And we could rotate this thing up and down, around like this. We could rotate it this way. We could rotate it around some line down here, right? Like we could rotate it like this or whatever. So what are we going to do? Well, this says find the volume of the solid formed when the region is rotated about the x-axis. Okay. So the axis of rotation is going to be y equals what? 0. Okay, that's the easiest of the sorts. So let's go back to last page, and let's again remind ourselves of this important formula right here. That's very important. Actually, I'm going to clip that out. I'm going to clip that out, and I'm going to, whoa, what am I doing? That page, thank you very much. Okay, I'm going to put that right up here so we can see that whenever we want to. Oh, goodness. All right. Okay, so this is going to be great. The x-axis is y equals 0. That's going to be our axis of rotation. So I'm just going to get rid of this just for space sake. But the volume of this solid of revolution. So remember, disks are pi r squared. That's the area. So remember, we always put pi out here. We're always going to have an integral. All right? And this integral is going to follow this little formula here that we have up top. So what are our limits of integration going to be? Well, we are going to take this area here is bounded by x equals -1 all the way to x equals what? 2. You see that? So my limits of integration are from 1 to 2. And the integral means I need to find an area. So the area here is represented by these two functions. Okay? So outer function first. Well, from the axis of symmetry, the outer function is going to be what? Y equals x plus 2. So I simply put x plus 2 as my function. Don't put the y. Don't put y equals. We're not putting the equals. We're just putting the description of this function. Okay? Remember, everything's in terms of x. Remember dx here? These are x's. This is dx. So guess what? The variable here has to be x as well. Okay? So everything is x in this situation. Excuse me. All right, and we also have to subtract the axis by which we are rotating this. The axis happens to be a constant of y equals what? 0. So that one's going to be pretty easy. And then we square that. And that's going to find us the whole thing here, all of this, the whole thing. Now, I don't want the whole thing because I don't want to include this part and this part. You see that? That is not included in my solid of revolution. So that's where this next part comes in. Let's subtract the inside parts. This is the inside volume that I do not want to include. So I put in x squared because that's the inner function. You see, the inside function x squared minus the axis of rotation 0, and that has to be squared. Okay, since this is your very first stab at this, I want to be sure that we're clear. So what are all the things that we talked about here? Well, if we are rotating this way so that the center of the discs are in line with the x-axis here, that means that this has to be x, this has to be an x, that has to be an x, and the variable inside need to be x, okay? So in this case, everything is in terms of x. There you go, beautiful. The other thing that we learned was pi r squared, right? So pi radius is this whole big thing here, and then the squareds, right? So pi r squared has to be represented there because discs are circles, we need the area of those discs. And then finally, to get, if there's an inside function that we're carving out empty space in this solid of revolution, then we need to include this full sort of representation here. Okay, this full representation, which means we may have to remove the solid that would be generated, and I'll just outline this, you see. So this is the empty space that we're carving out, you see. We're carving out this empty space in yellow. I don't want that. I just want the you know, if I'm doing a cross section of this three-dimensional, see? I want that, and I want that, and I want whatever rotates through space there. I don't want the middle part. So we have to subtract that away, okay? All right, am I overdoing it, or is that clear? Any questions there? Yes?
So if you have like x squared plus 1 and the parabola is like on 1, so would the axis be x squared minus 1?
Okay, yeah, so if the axis, you're talking about the axis of rotation?
Yes.
If that changes, and that will, we're gonna do some more examples where we do that exact thing, okay? So you'll see how that works. But yes, the nice thing is that we always just do this, subtract the axis of rotation. If it's up here, guess what? We subtract a large number. If it's down here, we subtract that. So we can do anything like that, and that's coming next. Another question? Okay, so you're asking about this. Why did we subtract here and here? Yeah. Yes? Okay, so these, because, okay. So maybe I will move over here to this one, okay? So what, look at, this is just the same thing, I just blew it up a bit. So the radius of the area, or the radius of what would be the disk, okay? Right, if this is my disk, look at what the radius is. I just want to find out what this area is, you see? So what is the radius? Well, the radius is function 1, which is this function, minus function 2. So it's actually from here, function 1, down to function 2. So if you take the value of function 1 minus the value of function 2, then you get this middle part, and that's your radius. So remember from yesterday, where were we? Yesterday, remember this? A better one. Oh, you know what? Here. Let's go back. Yesterday. Yeah, so right here. So see this? Remember the little fish shape here? Okay, that's f of x, and then this under here is g of x, right? So guess what? This distance between there is f of x minus g of x. So that's the radius, really, that we're using for our solid of revolution now. So that's why we have to subtract the upper function minus the lower function to find this area. Okay? All right. So let's keep going with this. And again, the nice thing about this is that we get to use our graphing calculator if we want, and you'll probably want to find out what this integral is. So v equals pi times. Now this right here, let's simplify this first. Okay, I'm going to simplify this. So this is going to be x, this is going to be just x plus 2 squared. And this is just going to be minus x squared. Right? You could simplify that further even. I would invite that. This is going to be x squared plus 4x plus 4, right? When you multiply that out, minus x squared, and so this actually, x squared plus 4x, sorry, what did I do?
Would it be like x to the 4 and the x squared? Like in the second?
Oh, I see, I forgot to square this at the end. Yeah, that's right. So this is going to be to the 4th. Thank you. So, yes, you're right. Thank you for that. So this is going to be negative x to the 4th plus x squared plus 4x plus 4. Now, if you didn't want to go that far, I'm totally fine with that, but the x. But now you can plug any of these into your graphing calculator and solve, okay? So pi times this integral. Two ways you could do that with a graphing calculator. You could graph it and then do second function calculate, or you could do on function just straight from the home screen. Either way, and we've been through that before, so I won't take too much time here on that. All right, so of course we could do this manually, right? This is actually not that hard to do, to find the antiderivatives of each of these terms. So this could be done by hand, but we've got our calculator involved, so we got about 45.24 units cubed, okay, for the volume of the solid. You guys get that? Awesome. All right. Okay, so that is really important. I hope that you're kind of on the right track with that. Let's do the next one here, and this is your question. What happens if we have a different axis? Okay, well that's no problem. Let's take a look at that. Instead of revolving around y equals 0 like we did on this question, what we're going to do is we're now going to revolve around y equals 4. So check this out. So this is our axis of revolution there. Now this is going to create this sort of thing. So this area now is going to rotate up and around this thing. So we're actually going to get some kind of like, we're going to get this sort of thing. Bad drawing, sorry. Okay. We're going to get this sort of thing, and that's going to be revolved around space there, you see? So you're going to get all of these disks that look like this, all this collection. So it's going to rotate up and around in space like that. So that's going to be your kind of your cross section. You see that? Okay, so how do we do that? Well, no problem actually. If we remember this that we have up above here, so let me copy that and bring her down. Actually, I'll throw it over here maybe somewhere. There we go. Okay, so all we do is we do volume is pi times the integral. Now, is the integral, are the limits of integration the same? Yeah, it looks like it. -1 over there all the way to 2. And now does the outer function change? Let's see. Let me just erase this here. Does the outer function change? Well, the one that's furthest away is going to be this one. So yeah, it sure does change. So that's the x squared one, isn't it? That's the outer function now. Minus the axis of rotation, that is y equals +4. So the +4 goes there. And then of course we've got to square that because we're still looking at pi r squared. Okay? So the radius is going to be the difference between x squared and 4. Also, though, we need to subtract the inner part here. So notice on my diagram over here, which is very cleverly drawn, very clear, not. But you see the stuff in red that I don't want would be all of this middle stuff, right? See, all that middle stuff I do not want as part of my solid of revolution. So let's go over here and get rid of that in between part. That's going to be my inner function, which is now my x plus 2, minus the axis of rotation squared dx. There you go. Okay. Now, if you're using your graphing calculator, totally fine. You can pump this whole thing in there. You do not have to do any simplification. Like I almost messed up with that to the 4th. So don't even bother. Just type it all in. No big deal. Get that into your calculator and see how that goes for you. So this is another question that we could do with manual integration. Expand all this out. You get a collection. You get some polynomial. All right. But my focus right now is just helping you to understand how we're going about this. Okay. Questions? Yep.
How would you know which one's the outer function?
How do you know which one? You got to have some kind of idea of the graph. Yep. So the outer function is the function that's furthest away from the axis of rotation. Furthest away always. Okay. So in that last case, like we just had there, this last case, which function is farthest away? Well, it's going to be this one, is the x squared one. The inside function is the one that's closest. Now, if you have something like, okay, let's say you have something like this, and you have something like this, and your a and your b, you know, like sad for you, but let's say the a and the b is like this, right? Ooh, okay. So now you have outer, and this is your axis of rotation right here. Okay, well, you're gonna have to split this up into two parts, no big deal. But this is going to be your first part, okay? You're gonna have to focus on this value, a to c, and you're gonna have to find this volume of rotation, right? This volume. And then you're gonna have to switch around and find this one, this volume that's like rotated, you see? Separately, because the outer functions change. So if they overlap each other like this, and your outer function, in quotes, changes, you're gonna have to split that up into two different sections. That make sense? Yeah. So find this one first, this one, this revolution first, and then find this next one, and add them together. Okay? All right? Okay. But let's not give ourselves nightmares about that just yet. Okay? You can have nightmares later about that. Okay? Not today. Right on. Okay, so what about this last one? You know what? I'm going to give you guys a chance to just do this on your own. Right here. This one. You guys do this all on your own. The line is y equals -2. And if I were to draw that, obviously over here would look like this line right here. And so if you were going to try and envision what this looks like, this is going to be flipped all the way around down to here, right? So it's going to look something like this. And it's going to be flipped around, boom, boom, right? So it's this thing passes through, you know, space like this and maps down to here and then passes through the other side and maps back to there. So it's going to be kind of like this, right? So it's going to rotate around this axis right here. All right? So go ahead and I'll let you work on this last part on your own. See if you can do it on your own. All right, so just once again, I did this one by hand here, manually, without the calculator, just to show you that it can be done. Just simplify, gather all like terms, and then go ahead and manually integrate. When you get to this point, it's not that hard to take the antiderivative of each term. Remember, evaluate it at the upper limit of integration, with the 2 in there, minus the lower limit of integration. Gather all that like terms. I skipped a couple steps in here, of course, but the exact answer, if you're looking for exact answers, right, this is 162 over 5 pi, and this one in decimal form, which you might have gotten with your calculator, is 101.79, and that would be cubic units, I guess. Okay, units cubed, units cubed. Okay, where are we at there? Okay. Okay, what I would encourage you to do, there is a second part of this where it's flipped around and we rotate about a vertical axis. I think I'm going to save that. We're out of time for today's lesson. So this is just around around a constant, a horizontal line, okay? So I'll get you to skip down to your day 62 homework here. And I'm going to get you to go ahead and start working on these ones. These are rotated about either the x-axis, okay, or a y equals line, okay? Now here is talking about rotated on the y-axis. You can just ignore that for now, okay? Ignore that for now. And work on the ones that rotate about a y equals line, okay? So for sure do number 1 here, okay? For sure do number 1 before the end of class, and we'll just double check your work there, okay? For sure number 1. Oh, sorry, and number 2. What did I just say? Oh yeah. No, number 1 and number 2 you can do, okay? Do number 1 and number 2 before you get out of here today, and I'll reveal the answers for you in a few minutes. All right, so for number 1, it asks for the coordinates for the intersection here, right? So the first coordinate is 0.1585, comma, negative 1.8414. And then B would be 3.14619 and comma 1.14619. So these are the same as day 63 homework that we actually just did. So the important part here is going to be A and B, right? Those are going to be used for your limits of integration for number 2. So number 2, here's the answer for number 2, and I'll just show you this as well. So you're going to have pi times, and of course this is going to be 0.15 here, this number right here, full number if you can, and 3.14, right, 169 or 619. So use the full thing, and then this is going to look like you know, the upper function, because y equals -3 is down here, so the outer function is going to be this ln 1, so it's ln of x, and then minus -3, right, minus your axis of rotation squared. Subtract from that the lower one minus the axis as well. So that's going to be your, what is it, x minus 2 minus -3 squared dx. Yeah, so you can simplify that a bit. Work this out. Calculator would be best. You should get this for your answer. Awesome. That wraps up today's lesson.